So this is some work. I've presented this preliminary versions of this before, but we're going to continue to work on this. And this is a new, well, relatively new optimization problem, certainly new before I started working on it. And the whole idea is that decisions made for engineering design will impact and affect the decisions that will be made for preventive maintenance or on-condition maintenance or any type of maintenance. And yet, the decisions are often made separately. An engineering design is developed, and then once that design is developed, a maintenance plan. If you're someone, say, in the aircraft engine or airplane industry, you would argue with me. You say, no, that's not true. And I would say, you're right, because in many industries, they do consider that. But if you look at the engineering journals, if you look at the research, and you look at the analytical optimization models, they're often separate. In fact, almost always separate. You have plenty of good work for design optimization, and you have many good work for maintenance planning, on condition maintenance, but they tend to be separate. So my goal here, and this is something now I've worked on about 5 years and then can continue to work on, is to combine them. Okay, I'll do this briefly, but as Professor Chen said, I come from Rutgers University. I very much had planned to give this seminar presentation in person. We had made plans for me to visit Nanjing, and I would also visit other universities. But here I am in New Jersey. So if you look at the red circle at the bottom of the screen, that's the state of New Jersey. And if you look at the map, I'm at what's labeled Rutgers, New Brunswick. That's the main campus. And I'm hoping some of you know Rutgers. I know some of you do. But if not, let me just say briefly, you know, we're at Rutgers, New Brunswick. That's the main campus. In terms of enrollment, we're one of the largest universities in the eastern part of America. We're the state university or public university of the state of New Jersey. We're also one of the very oldest universities in America. I know the history of America is recent compared to the history of China, but Rutgers was actually formed as a university before our country was formed. So Rutgers was formed in 1766. It was called Queen's College, which is 10 years before actually the country was formed. So, and everyone there is welcome to visit me. Now, first, I'll just talk about myself. I've been a professor at Rutgers now over 20 years. And the whole time I've been there, my primary research has been some form of reliability or system reliability. And it still is. I do other things, but my primary research is system reliability modeling and optimization. Quickly, some of my students, Jen Zhou, Nushen Yusefi, a very good master's student, Jianhong Li. I think I saw him maybe sign on, and he's very good, defend his master's thesis soon. Collaborators include people like Shenmei Feng from University of Houston, Xiaoyan Zhou from UCAS, or University Chinese Academy of Science, Yisha Xiang from Texas Tech, and I'll skip this, but we typically do systems reliability, and lately systems of degrading components. And we've done many types of analyses. Now, today's talk won't be on this, but over the last 5 or 6 years, or even longer, about 50% of my research is on electrical power grid optimization. And It started with my work in reliability. I was asked to do reliability work on the electricity distribution system that brings electricity into your home. But pretty soon we were doing other types of optimization work. And in fact, now many of our projects don't have anything to do with reliability. We're looking at very interesting work. In the future, as the demand for electricity is changing and also the needs of society are changing, how do we optimally expand the grid? And, we're looking at many interesting things, societal health costs, climate change, and in large part, minimization of greenhouse gases. So these are the types of research I do. I've presented many times my research at different universities in China. I suspect many of you have met me. If not, I look forward to when we can meet. Now, for today's talk, these are the people who have mostly worked on this. This work started with the woman in the middle, who is now Dr. Nida Chatwattanasiri. And one thing, being an engineering professor in America, and I know I don't say any of the names right, but you learn to say the names in many different languages. Nida is from Thailand, and right now she's a researcher. So it started with her. And then in 2016 and 2019, last year, I had a invited research position at University Chinese Academy of Science in Beijing, where we continued to work on that. And the handsome gentleman to the right of Nida, Xiaoqiang, started working on this, and he's now a PhD student at Tsinghua University. And then on the far, I left out my colleague at UCAS, Xiaoyan Zhu, and she's the one who invited me to UCAS and has worked with me. And she gave a very nice keynote address at MMR in Hong Kong last year that has some of the similarities to my talk today. And then on the far right is Jian Zhou, and he's doing my recent work that I may not even get to. It's right at the end of today's presentation, where again, we're focusing on the electrical power grid, and we're saying, can we do system hardening? And that's a term we use in America just for the electrical power system. Hardening, it's just the way it sounds, hardening, make it stronger, make it tougher. But really it means make it more reliable. And how do you combine system hardening with system restoration policy when you get hit with something like a flood or a hurricane or a tsunami? And Jian Zhou is working on that right now. He'll be finishing his PhD soon, very soon, within several weeks. Now here's my talk today. Here's the outline. Let me just get into it. And as I said, we're taking two analyses, redundancy allocation problem, and then preventive maintenance planning that are typically done separately, and we're combining them. Now, those of you who know my research, I don't typically work in this very much anymore, but I certainly did in the early parts of my career. In fact, my own PhD dissertation from University of Pittsburgh was on various forms of the redundancy allocation problem given uncertainty, estimation uncertainty primarily, but other types of uncertainty as well. But just very briefly, we have system reliability, but we have a design vector given here as X that we can change the design. We can decide which components we will use, perhaps which architecture, in other words, how to design it. Perhaps, not perhaps, but always, how much redundancy, where redundancy means instead of using a more reliable component, we're going to use two less reliable components, or more than two, and place them in a parallel structure such that if one failed, the other one can do the job. And now look at the diagram at the bottom. In fact, it's not a very good diagram in one sense. We have S primary functions which need to be performed. And for each of those functions, though, I can add redundancy. And you see M1, M2, MS. Now, the reason I say I don't like this diagram, because it implies the way it looks that M1 is equal to M2 is equal to MS. And that's not true at all. In fact, for many of the subsystems, we don't need any redundancy. They're fine. And in fact, for most commercial products, or at least many, or yeah, most, you don't need redundancy. They're either sufficiently reliable or they're not that important, meaning if they fail, you get them repaired or you just get a new one. But for many high reliability products, redundancy is important. Now, there's been hundreds, maybe thousands of papers written on this, but 95% of them, and that's a guess, have been a deterministic model. And what does that really mean? It means before you start, you know the reliability of the components within the system. Well, I've said many times, that's pretty difficult. You know, I can look up a cost, I can get a scale and get a weight, how much something weighs, and I can measure other performance parameters, but I don't have a scale to measure reliability. I have to conduct a test or look at some field data, and there's always uncertainty with that. So I think the first paper might have been by me, or in the late 1990s. I said, well, let's treat that as a random variable, stochastic parameter, stochastic function of the design vector X. And that's what I say is one-stage stochastic model. And now more recently, we're doing what's called two-stage stochastic model, or more specifically, two-stage stochastic programming with recourse. And that's mostly today's talk. And you see some of the papers we have there. And I added the paper we're working on right now, Jen Zhou, as part of his dissertation. Now, I'm not going to go over this list, but here's just some of my recent publications in this area for the last several years. And then if you went back beyond the last several years, there'd be many more. Professor Chen said, when she introduced me, I have many, many publications. So this is an area I've worked in, many times. Now, the next area is preventive maintenance planning. Now, that can mean many things, and some people use a very specific definition for preventive maintenance, and I do not. I'm using kind of a general term. It could be a time-based preventive maintenance. It could be on condition. My talk today doesn't focus on predictive maintenance, although maybe next year, if I give a talk, it will. But for preventive maintenance planning, you have different decision variables. When to perform maintenance, when to perform an inspection, what intervals. Are the intervals static, meaning they're not changing once you get a good one, or dynamic? And often these problems are formulated as usually some form of nonlinear optimization problem. You look at the graph there, I have cost versus preventive maintenance interval for several different possibilities, and you want to find the area to minimize cost. This is the simplest form of the model, which is mostly what I'll be talking about today, where we're just going to select the optimal time. And I've also written many papers in this, and these are all papers that are on preventive maintenance planning, all since 2017, I guess. So I've worked in both of these areas, so it seems I'm a logical one to combine them. Now, listen, this is my philosophy. This is Professor Coit's philosophy. See that shape I have there on the screen? That's a big project. Or you could think of it as a big problem. It's a big project. The project is too big. I don't know how to solve it. It's too big. Or it even could be a big problem, like say a problem in your personal life. You have girlfriend problem and problems with school and family. Maybe you're sick. If a problem or a project is too big, it's difficult to solve. So how do we solve it? We take the big project and we break it into small projects, right? Because each small project, I can put the other ones out of my mind and solve them. So we break the big project into small projects, and then one by one, I can start to solve the big project. See that little shape there that's kind of a arrow? That means I've solved that little project. But what happens? When I solve one little project or solve one little problem, it creates constraints for the other ones. And those little arrows mean because I've already made some decisions, the next projects I'm going to solve, smaller ones, I have to accommodate or I have to consider the decisions that have already been made. And then when I solve those projects, I continue to add constraints such that by the time I get to the final projects, which are over here, maybe I can't get really good solutions because of the decisions that have already been made up there. Now, first let me ask you, is this a good way to solve really big projects? And the answer is yes, of course it is. Airplanes are built this way. Big buildings are built this way. You take big projects and you break them into small projects because you know how to solve them. So is it a good approach? Yeah, sure. But what's going on? When I take large projects that are too big to solve, I break them into small projects and I solve each small project individually. But what happens? The solutions of each subproblem creates constraints for the other subproblems. Okay, let's continue that thought. Now, this is the same diagram. These are maybe the last two projects I'm going to solve. The yellow one, once I solve that, it creates constraints for the purple one. Well, what happens if and perhaps the decisions I make in yellow are not so good for purple. But what happens if I can combine those two? Would you agree? I can get better solutions for the two that I combine. Because when I make the decisions for yellow, I can consider, well, what's going to happen to purple? So that's my philosophy for today. So the combined optimal solutions, when I solve each subproblem individually, are most likely not optimal for the whole big system. They could be, but often or most likely not. So if I can combine some subproblems, perhaps use computing power, I can get better solutions. And what's my example? In red down at the bottom, system redundancy, allocation, and maintenance planning. Now, right now, system design or redundancy allocation problem is typically done separately, and it of course impacts the life cycle cost. Preventive maintenance planning is done usually given a design, and it impacts the system life cycle cost. But if I can integrate and combine them, I can perhaps have even lower life cycle cost of the system. Now, a little more formally, and again, the models I showed today are a simplification. Redundancy allocation problem is just one, fairly straightforward problem. But I'm trying to use that as an example for a larger problem, a bigger issue, I should say. because system design has many things beyond redundancy allocation. But that is one problem. So my talk today corresponds to any type of analytical system level design. So I could have redundancy allocation or reliability allocation, where the reliability values themselves are decision variables, and I have different types of decision variables. But what happens traditionally is when I finish my system design and I'll look at the arrow, it's sequential. Those decisions have been made. And now I do maintenance optimization. Now, once again, I know darn well that in many industries, they consider how this is going to be maintained when they're doing their design. I know that, of course they do. But if you look at the engineering journals, the reliability journals, the types of journals that I write papers for, and that many of you people do too, they're not considered together, or rarely. And that's because when they are considered together, it's usually not through some sort of a rigorous engineering model. So we have the arrow going one way. Now watch my slide. I want to bring them together and have this integrated research plan. And later today, and I probably have more slides. I might have more slides than I have time for, although I hope not. I hope I can finish. But this is what I'm going to call first and second stage for my two-stage stochastic optimization. And at the end of today's talk, I'm going to say, once the system has been fielded, I can start getting better data. I can start taking the assumptions I made to do system design and maintenance optimization, which might be based on the best information available, and that might not be that good. But then I can continue to update, and that's what I call third stage, or update maintenance optimization. And then I might even, although I don't want to because it's costly, I might even, based on the data I collect, realize I need to change the design, and that's what we call fourth stage. Okay, our combined model. So I think my student Nida, that's now Dr. Chatwattanasiri, started working on this. And at first I wasn't sure, but I asked her, try to find examples where design decisions have to be made, yet the future has sufficient uncertainty that we're making decisions based on the best available information. But the uncertainty creates, different issues. We can't estimate reliability given the uncertainty of the stresses. And so one example we came up with is electrical power grid. And as I've said, I work in this area where we don't know, in America anyways, we're getting more and more what we call extreme events. Those are floods, hurricanes, very hot weather. And although there's people who deny it, it seems like it seems like it's getting worse and worse. And so the future, the environment is changing. Although I hope not, but it sure seems to be. And so, but we don't know. We don't know. And yet design decisions have to be made. And those design decisions are based on reliability. Well, we continue to look at it, and we realize there's many examples. This is one where you have to take an airplane in just a very short duration, launch it into the air. And so there's a specific system, an aircraft launcher. But that aircraft launcher depends on the nature of the airplanes. And as airplanes are getting heavier, faster, the stresses on that aircraft launcher change. So now you look to the, and we wrote 2 papers on this. There were papers at the RAMS conference in America I go to every year. Unfortunately, it always takes place during the Spring Festival in China. But there's always There's always some people come. And so what I show there is, that's the Greek letter eta. And for the rest of my talk today, the Greek letter eta will be a Weibull scale parameter. But you see this equation where I say the Weibull scale parameter is actually a mathematical function of the speed of the airplanes and the weight. And I should add, although I don't say it here, that's the average speed and the average weight, because the launcher might be launching different planes, same launcher, a heavy one, a light one, a heavy one, a light one, all on the same day. We continue to look at the electrical power grid, the components in this system. The Weibull scale parameter might in fact vary based on the mean temperature, the number of extreme events, which that's the term we use for floods and things like that. You may have these data centers. You know, data center is where all big financial institutions have their data backed up. And you have these data centers that are just full of computers, although I guess they're now moving into the cloud, but and they have, you know, hard drives, just thousands of them. And as the data center gets used, you know, the load and the temperature environment, it's also going to impact it. And, you know, we might know the future, we might not, and on and on. Even simply something like a mechanical system of bearings. Perhaps the system has unknown future usage. You know, we don't know the applications it's going to go into. And therefore, but our models require perhaps a Weibull distribution, a Weibull time to failure distribution with a scale parameter and shape parameter, and yet they could be, and often they are, even if we don't consider it, a function of the stresses that it's going to be exposed to. Now, this is just for guidance. The stresses could be anything. And that's the point I'm going to try to make here. And by the way, I use the word stress like an industrial engineer, which is interesting, because I have 4 university degrees. My first degree is actually in mechanical engineering from Cornell University. And when you're a mechanical engineer, of course, stress has a very specific meaning in mechanical engineering. I'm not using it that way. I mean, stress is any influence, whether it's operational or environmental, that will cause an item to fail sooner, or perhaps the opposite, not so soon. So this is just for guidance. I don't need to classify them, but it could be environment, temperature, humidity. It could be the stresses, the mechanical stresses, like in the bearing example, you know, the actual physical load. It could be the usage. How often am I going to use this? And at what speed? Now, I haven't introduced much notation yet, but I'm going to soon. You see at the bottom of the screen, I see vector U. Vector U is a vector of C different stress variables. Now, I'm going to introduce notation, and the rest of the presentation will use this notation. And if you know me, if you know me, it's hard for me to go this long without any equations, although I had a few. Now, you're going to have to learn, if you learn a few simple rules about my notation, it will make it easy to understand. A capital letter or a big letter means it's random. It's random. I don't know what it is. It's a random variable, perhaps with a distribution. If I use a small letter, it is not random. That means it's a specific value may be chosen from that distribution or observed. The second rule, if it's bold, like that bold letter U, bold or dark, it's a vector. If it's not bold, it's not a vector. Okay, so if you can remember those simple rules, so I have a vector of stresses. How many stresses? Small c. Now, how many different possible u vectors are there, given those are c different random variables? Well, probably infinite. Probably infinite. You could think of a c dimension joint probability density function. So there's probably an infinite number. And infinite's a lot. So of the infinite number, I'm going to select some typical ones. And the typical ones I select, we call them scenarios. So I select the scenarios. I can select a lot. I can select a few. The C stress variables, those are, well, a decision has been made, but those are fixed. Now, each stress variable might not influence every component. That's fine. But the number of scenarios is something I select. And probably someone will ask me, how many should I select? And unfortunately, I don't have a great answer because it's a trade-off. If you select lots of scenarios, potentially your model is better. It has more fidelity. If you know that word, it's more accurate. It will be harder to solve because the problem becomes bigger, but it might also be harder to estimate those scenarios. If I choose a few number of scenarios, my model is perhaps not as good, but I can estimate the scenarios very well. So it's a trade-off. But right now, if you look at in the middle of the slide, I have vector u1, vector ul, vector uv. Notice those are not big letters. Those are small letters. And those are bold. So those are all vectors. And those are v different vectors that I've chosen to represent the uncertainty in capital U, which is random. So think of it, it's a random distribution of c variables. And I'm choosing v possible outcomes. And each of the outcomes, if you look up in the kind of box, I've assigned, and I'm going to use the word likelihood. Okay, sure. P stands for probability. I won't deny that. But I'm probably not going to know these probabilities exactly. So I'm going to call them likelihoods. These are how likely I think these scenarios are going to occur. So to summarize those thoughts, if you look at it this way, we see this is, if you can understand this, you'll probably understand my notation for the rest of the talk. I've got this random vector, capital U, and I'm going to, where there's an infinite number of outcomes. But I'm going to, in my model, say it's going to be one of these V scenarios, where each of the V scenarios are fixed vectors. Now, I don't know which one, and I need to select V big enough so that it approximates the random distribution of capital U. So this slide is very important. We have this idea of scenarios, and we have this idea of different stress variables. So here's a small example. I might say there's 3 different variables, and I'm going to pick just 2 scenarios to represent them. So I have 2 vectors, and I'm going to say random U could be one of them, could be one of those 2. Now here's 2 examples. The upper table is from a paper in 2016 about climate change for the electrical power grid. Now this is a perfect example. Climate change takes place in the future. I can't collect data on the future, but different scientists have made projections as to what they think it can be. And so we looked at the worst case projection, call that scenario 1, the best case projection, which is scenario 5, and then some in between. So 5 doesn't seem like a very high number, but these were ones I could estimate very well. The one on the bottom is another example where the different loads on a part. Okay, now just quick summary. I don't know my audience here, but the most popular distribution for failure time is the Weibull distribution. I'm going to use what is typically the most common notation, but there's different forms of the Weibull distribution. I have a shape parameter, which is beta, a scale parameter, which is the Greek letter eta. Those of us who work in reliability, we love the Weibull distribution because I can have many different shapes for my probability density function. The graph you see is a typical probability density function. Now at the bottom, if you don't know the equation, take a look at it. And let me get my highlighter out again. So that you see how the reliability function, and now I'm breaking my rule a little. I typically will use a small r when I'm talking about a component, a part, and a big R for the whole system. So that's breaking my rule a little bit, but this is the equation we need to know. But as I said, this eta term, that could vary with stress. Now I know some people may say, and I know one listening, can't beta vary with stress too? And the answer is yes, it could. So why didn't I include that in my model? Well, if you look at my hands, if you can see me, if the acceleration is linear, meaning as the probability density function expands or contracts, if it does it in an entirely linear way, then beta will remain constant. And so that's an assumption I have made that's very typical for accelerated life testing. Okay, I got to get rid of my laser pointer. Let me move ahead now. Take everything I've talked about. You just saw the equation for reliability. But now I'm saying I don't know the future stress. And the reliability of a component is a function of this future stress. Now it's a new notation, I and J. I is for the ith subsystem. So if it's an airplane, I have some communications, I have some radar, I have some propulsion, I have some other things. I is subsystem. J is which component will I use in that subsystem? And so you see eta ij, but eta ij is a function of u, and beta ij. Now, I've got these scenarios. The v different scenarios are selected to represent the uncertainty, but each of the v scenarios is a fixed vector. So I can substitute in for the ELF scenario and have a reliability expression. It doesn't really matter for today's talk, but I've scaled all the stresses from 0 to 1, and I've scaled the current stresses so that they're all zeros. That's just a mathematical scaling. It doesn't really, you can always do that. Now, how am I going to relate U, the stress vector, to eta, the Weibull scale parameter? And at the bottom of the screen, you see the way I do it and a new parameter, alpha ijk. Listen carefully. Alpha ijk. How much does the kth stress impact the jth component choice for the ith subsystem? If alpha ijk is 0, that component is not affected at all by changes in the stress. If alpha ijk is a high number, that means as that stress changes, the Weibull shape parameter changes a lot. Now, if you look at the functional form, I chose that such that eta will never get negative. And of course, keep in mind, I can take log of the stress. I can take the inverse of the stress. I can take many transformations. Okay, continuing, I can now construct a system model. This is for a series parallel system. I can have the system reliability, a function of the random stress. I can have the system reliability for the stress in one specific scenario or one combination of stress variables. And furthermore, I can take the expected value of the system reliability considering the uncertain stress. And that's easy to do with scenarios. I just sum over the scenarios, and that PL, which I chose to call likelihood, but we're using it in this equation clearly as a reliability. Here's the first paper we wrote. This comes from the work I did at the UCAS, University Chinese Academy of Science. Xiaoqiang Bei was kind of assigned to help me. And oh no, excuse me. This is oh, I'm ahead of myself. This is the paper we wrote before that happened. And this is the first paper we wrote, just with Nida Chatwattanasiri and another friend from Thailand. And I'm really proud of this. If there's anyone from Thailand listening, I'm sure I don't say it right, but it's close. Naruman Wattanapongsakorn. Okay, yeah, that's the first paper we wrote where we used the model I just showed you from 2016. Now we move to the work that we started at UCAS in 2016. And here's where we're formulating this as two-stage stochastic programming with recourse. If you don't know what that is, there's a famous textbook by John Burge and his co-author. But for two-stage stochastic programming, you take your variables and you split them into two categories: first stage, second stage. The first stage variables are those decisions that have to be made given this uncertainty that you don't know. And for us, those are the design variables. The second stage variables are those variables that you can wait and see what the uncertain outcome is. Oh, it's more stressful than I thought. Oh, it's less stressful. And then you can adjust. So for our model, that's the maintenance decisions. I can adjust. Oh, wait longer to do preventive maintenance. It's less stressful than we thought. But for design, you have to make your design decisions given your knowledge of the uncertainty and the knowledge that any of these uncertain outcomes could occur. And so we formulated this problem as this stochastic programming problem. And if you look down at the bottom, we got three good journal papers out of this, 2017, 18, and 19. Two different journals, but very good ones, where we're considering the system design and preventive maintenance planning together as this two-stage stochastic programming with recourse. First stage, selection of the components and the numbers to use in redundancy. Now, we're going to solve these together. But the first stage, we need to decide these before the specific usage scenario or stress is known. But once it is known, the second stage decision variables can be customized or specific to the different, to the specific scenario of stress that was observed. Okay, here's the paper. This is a 2017 paper in IEEE Transactions on Reliability, and this was our first model. Now, this is our formulation. Let me see if I can find that highlighter. So, let me turn it back off. So in the objective function, we have the cost rate, but now I don't know if you use this notation in China, this right here, the A/PIN. This is how we're going to mathematically convert using the concepts of engineering economics. We're going to convert, simple formula, a fixed cost, a fixed present cost into a equivalent series of costs over time, or an annuity, which is a series of costs over time. So by multiplying that by the APIN, I've taken that fixed cost and determined an equivalent stream of costs. And then I add to it the expected maintenance cost rate given the uncertainty in U. And as examples, I just have a constraint for cost, system cost, and a constraint for system weight. The constraints could be many things. This was just an example to demonstrate that we can actually do this. Now, we have this expected maintenance cost rate. Well, we're assuming the maintenance cost rate. First, we sum over the various subsystems in the system. That might not be right, but we're assuming that the cost to fix the overall system is the sum of fixing the individuals. And these are cost rates, cost per time. But it's an expected value. So I then, given I have scenarios, I can then just sum over the scenarios and those likelihood, which is P superscript L, the likelihood of scenario L. Now, this is what's referred to as my recourse function, meaning the maintenance cost rate for each scenario is another optimization problem, because I can select the preventive maintenance, and this is just a simple form where we're going to replace the subsystem components at some time YIL. So YIL, that means subsystem I, scenario L. Now notice if we go back up, the X variables didn't have an L superscript because they're the same, whatever scenario is observed. But the preventive maintenance, they do change. And so this maintenance cost rate is actually another optimization problem. I'm going to minimize and get the minimum cost rate by adjusting that preventive maintenance interval. Well, I can combine all that together and get this model. And it's kind of it's not kind of confusing, it's confusing. But what we have there, it's actually, if you took the time, somewhat simple. All I'm doing, I'm assuming that when we replace one subsystem, it's replaced with another one. And so the cost rate, I can simply look at the cost for one replacement interval divided by the expected time of that replacement interval. And I guess I'm going to run out of time if I really explain this all, but if I replace it preventatively, there'll be one cost. However, if I don't replace it preventatively and it fails before the Y, which is a decision variable, then I've got a higher cost. And you see that CI superscript F. Well, this is a hard problem. It's got everything. It's probably non-convex. It's intractable. It's nonlinear. It's a hard problem to solve. So at the time, and we've done other things since, we looked at these derivative-free optimization, kind of black box solvers. And these are examples of publicly available black box solvers. So derivative-free. I don't want to take the derivative of that equation. So these are publicly available. I believe they're all free. We got them when I was in China. And we said, the student said, well, which one should we use? I said, well, we don't know. We don't know which one's best. Use them all, which made his work go up by about a factor of 5. But now we'll show some examples. This first example is very small. It's just to demonstrate. I just have one subsystem and 3 possible components. There are 3 stress variables, K equals 1, K equals 2, K equals 3, that influence the rate with which these components fail. Now I have 4 scenarios. Once again, there might be an infinite number of possible outcomes of these variables, but I'm selecting 4. Now this is just to demonstrate. I would really want more than 4, but this is to demonstrate. And you look at the 4 of them, you see the stresses are increasing. Once again, the stresses, we don't have to do this, but we scaled them from 0 to 1. So we solve this using these, first, here's the expected component reliability. The one that's most reliable, and again, expected value, is most expensive. Well, that's typical. So there's trade-offs involved. So we solve this using these various derivative-free optimization methods. We see the objective function there in the second column. And now we don't know what the optimal solution is, but we get our best solution with ease. And you look at the far right, we have computation time. So when you look at in the middle, you have the optimal solution. It seems like a fairly simple solution. We just use 3 of the third component. But you look at the very first row, we have an objective function that's not too far off with a very different solution. Now, you look at the y's, and we have 4 of them, because remember, this is 2-stage stochastic optimization. I need to pick a design not knowing which scenario will happen. But once I observe scenario, I can selectively pick the preventive maintenance time. So in my optimization model, I have a separate preventive maintenance time for each scenario. And then if the system is fielded, a scenario occurs, I have the corresponding preventive time. Okay, so we've solved this problem. Is it a good solution? I think so. 3 of the solvers went to the same solution. Can I prove that it's optimal? No. I would love to do maybe some sort of convexity proof or something, but I think it would be difficult to do. So now we're gonna, okay, so here is the 3 components. I'm sorry, this is the system cost rate, and then this shows for each scenario where the optimal replacement time is. Keep in mind, this is a simple system with just one subsystem. Okay, now we're going to go to a much bigger system. 7 subsystems, and for each subsystem, I can have 3 component types. Now, you might think that doesn't sound so big, but when I choose the components in the subsystems, I can match, I can mix, I can have 2 of this component, 1 of this, 2 of this, 3 of this. This is actually a huge combinatorial problem. I think you'd be very surprised if you enumerate, well, you could not enumerate all possible outcomes. There's too many of them. You know, particularly if you don't limit the amount of, well, we have constraints, so we can't have too much redundancy, but so we have 7 subsystems, 3 component choices for each. We have 3 stresses again and 4 scenarios again. Now these stresses are system level stresses. So I don't have a separate stress vector for the components. I have a separate alpha, which is the sensitivity. And so we have these other parameters, the alpha sensitivity parameters. We have the Weibull distributions and cost. Now I go ahead and solve it. Now, I don't necessarily expect you to remember. Actually, let me go back. So Nomad, the GLC direct and GLC cluster were the best. GLC direct and GLC cluster had significantly shortest, smallest computation time. This NHS was not the best, but it was close. Now let's go to the big problem. The ones that were best for the small problem are terrible. And in fact, some of them won't converge at all. And look at the computation time. Nomad, which had the best solution for the small problem, actually does not have the best, but it's close. And its computation time is somewhat reasonable. The NHS, which was not the best for the small problem, but is the best for the bigger problem. What's my conclusion? Right now, I don't have one. I don't have one, other than based on this one simple example, well, two simple examples. It seems like Nomad was the most robust for these derivative-free optimization. Let me move more quickly. Professor Chen gave me an hour and a half, but I need to end. Time for questions. Now, we did all this work, all these equations, and then the issue is, did we really come up with a better solution? The whole idea was, if you do design and maintenance planning together, I'll get a better solution than if you do them separately and sequentially. Well, we haven't demonstrated that yet. I think the student was so happy we finally got some results that when I said, well, we haven't actually done anything until we prove it, it was kind of a disappointment. So we went and did that. We first solved a reliability optimization problem. Then, given that design, we solved the minimum cost. I may have some problems in this table, but the column to the far right is correct. Now you look at the bottom one for case number 4, the percentage saving 0. So I think the student was afraid to show those to me. That says if I did the sequential design and then maintenance planning, I get the same solution. Well, that's not surprising. That sometimes it does work. What's interesting, though, is that the times when the combined plan does give you savings, and that was my whole point from whenever I thought of this research. I don't know, when the first time it came to me that this would be worth doing, and at first I presented it to Nida and then to Professor Zhu and Xiaoqiang. Now, that's our first model. We've extended this a number of times. I'll just kind of review these quickly. The first extension, one weakness with what I've just showed you is that although the stresses are random, they're stationary, meaning they're not getting worse or better. Now, I don't know if you noticed that, but the stresses were not a function of time. So our first extension was to remedy that, to have the stresses changing with time. And for the examples we used in the paper, and it was published in 2018, IEEE Transactions on Reliability, the stresses were always increasing in time, although the model would work otherwise. Another interesting thing with this paper was that the inspection intervals are not, they're not static, they're dynamic, they're changing. As time goes on until you replace it, you'll inspect more often. Once again, we assume stresses were getting worse. If they're getting better, you would probably observe the opposite trend. So that was our first extension. The next extension, published just last year, European Journal of Operations Research, this is this idea of risk aversion. If you've known my research, I've done, maybe not a lot, but several papers on risk aversion. What's risk aversion? First of all, what's the word averse mean? We have two words in English that sound a lot alike, averse and adverse. Adverse means bad. Adverse weather. Oh, it's raining. Averse means you're afraid of something or you want to avoid something. Averse would be the adjective. Aversion is the noun. If I have an aversion to snakes, that means I hate snakes. I run whenever I see snakes. So when we say risk averse, that means I'm afraid of risk. I want to avoid risk, just like I want to avoid snakes. So if I'm a risk averse decision maker, I'm not worried. Well, no, I still care about the expected value of my random objective function, but that's not enough because I'm worried about how bad it could be. Here's the way I explain risk aversion to my students. If you're going to get on an airplane, you're about ready to board an airplane, and they told you when you entered, this airplane is very reliable, you would say, great, and you would step on the airplane. Now, the next day, they say, this airplane is very reliable on average. Some are, some aren't. Whoa, you would step back off. You would say, what do you mean? Very reliable on average? This one might be less than average. So if you think like that, you're risk averse. You're worried about how bad it could be. So our second extension is let's solve this risk averse. Let's make decisions to minimize cost, but we're concerned not with the expected value like the other papers, but how bad it could be. And we use the concept of conditional value at risk, or CVAR. That's a common term used in the finance industry, CVAR. Objective function. So let me move on now. Model extension number 3. We're working on this right now. In fact, literally today. So you see I have identified a journal paper, Zhenzhou, myself, Frank Felder, who's the director of the Energy Center at Rutgers University, and I say under preparation, and that's true. And here is where our system design will be what's called system hardening of the electrical power grid. And those will be stage 1 variables. And then restoration means if there's an extreme event like a flood that causes the electrical distribution to fail, so there's no electricity, how can you restore it? And there's different restoration policies. Do I restore the largest customers first? Do I restore based on what's easiest to fix? Do I restore which components are most critically located within the system? And what we're saying is, depending on how we do system hardening, the restoration policies for a given extreme event might be different. So I'll skip the details because I got some other things to talk about. But that's what we're working on now. And here's a slide Zhenzhou prepared for me. We have electrical power grid. We have customers. This is you and me. We use electricity. Could be wherever you are right now. Since you're listening to me, you're using some form of electricity. So we're customers, and we're called load. The customer is the load. Then I have the big generation units. And the big ones, a nuclear power plant or a coal burning plant. And then I have transmission lines. These are the high power lines. Notice the transmission lines don't go all the way to the customer. They go to a substation where the people are. And then now notice the smaller lines, that's distribution. Those are the power lines you see coming into your building, coming into your home. Now, when you have extreme events, you may have a dependency cluster, meaning if one of these fails, the other ones in the cluster are more likely to fail too. They fail as a group. That's called cascading failures. And we want to do some hardening within the dependency cluster, get those more reliable. And at the same time, choose restoration policies, given we don't know the extreme event that will happen next. So this is our next extension. I'll go about 10 more minutes. I hope that's okay, Professor Shen. The final thing, and these are mostly ideas. Now, we've done some work and actually have some numerical results, but these are mostly ideas. If someone wants to steal my ideas, they can. I'm always looking for collaborators. But now, data-driven optimization for redundancy allocation problem and preventive maintenance planning. Everything I've talked about today so far is what's done before they're planning models, before the system is fielded and we start collecting real data. You know, I have a preventive maintenance plan for different scenarios, but it's still based on estimates of all these parameters. And I can do the best I can to estimate these parameters, collect some data, look at some similar components, but it's difficult. Now, let's say I've estimated all those parameters, I've solved my model, but now the system is put into the field and I'm getting real data. And I'll quickly go over 1 and 2. 2 is what I want to work on in 2021, 2022. Haven't really started it, other than I've done the math. Number 1 is just what I've already showed you, but now data-driven and adaptive. Number 2 takes everything we've talked about today and switches it fundamentally using degradation models like a gamma process or an inverse Gaussian distribution, or excuse me, inverse Gaussian process, and have much better maintenance policies based on unconditioned maintenance or maybe even predictive maintenance. So this is number 1, adaptive and iterative design and maintenance models. You see what's labeled present time. That's what you've listened to today. That's what you've heard me talk about today. But now the system goes into operation. I start collecting data. Now, what do I mean by data? It could be data on the environmental stresses. Maybe those scenarios I estimated weren't right. It could be data on failure times. It could be data on degradation, although that's more in number 2. So I've got data, and that's what we mean by that graph up there, which means I can update all of those parameters in my model. And this is what I call third stage. Now, I've already made design decisions. It's too late. But I can continue to update those preventive maintenance intervals. Probably not all the time, but that's a management decision. But now, as I'm collecting data, I can update the preventive maintenance, and I can go to my 4th stage. Once again, I don't want to change the cost. I don't want to change the design. It'll be costly. But stage 4 says, well, what if I do change it? What if I do change it? Will there be cost savings? And eventually, the cost savings might be big enough that I go back to 1 and 2. And this is what we call the 4-stage plan. Right now, it's mostly just an idea. So the 3rd stage, I'm updating these parameters, which allows me to change the maintenance plan. And I introduce some notations here, capital L. This is for the new scenario I'm actually observing by my fielded equipment. I'll skip over these. I told my student, just use Bayesian updating. We have a Bayesian prior distribution, and we're going to update it using the available data to get a Bayesian posterior distribution. And I don't teach or do research in this area, so I told my student, keep it straightforward. Just do what other researchers have done. But we have the prior distributions, which allow me then to update the parameters in the model. So you see there, I have a new beta, I have a new eta 0. In my preliminary work, just so we can solve this, we assumed the alpha IJKs were correct, and we did not try to update them. It just became much too difficult of an estimation problem to update everything. But in practice, I would need to do that. So I have my new betas, but now I no longer have a two-stage stochastic optimization problem. It's actually still nonlinear and non-convex, but it's actually an easier problem because it's only a function of, I only need to minimize over those y, the preventive maintenance intervals. So I can do that. Then I go to this fourth stage. And again, the fourth stage is monitoring. I don't want to change the design. In fact, I'm hoping, I already selected a design that will supposedly minimize cost. But if my estimates for parameters were bad, I might need to. But I have this threshold. The cost savings better be large. But if they are large enough, then a recommendation goes to management. You might want to consider changing the design. You know, I teach linear optimization, usually in the fall. This semester, I taught nonlinear optimization in the spring, and then an applied optimization class for master's students. And I often tell the students, I say, you know, I want you to be interested in this work, but you have to remember, we're analysts. We're not the decision makers. What we can do is solve these problems and make recommendations to the decision makers. And that's what this is doing. So do we change the design? Well, our model doesn't make that decision. Our model simply says these are the available cost savings. And so we have a new objective function. This is just the cost rate prior to changing the design, and then a new cost rate with the double, notice the double prime with a new design vector, which then also will translate to a new preventive maintenance interval. I won't worry about the mathematics. Now, and so we can do that. Now, in my final 5 minutes, here's what I want to be working on next year, and perhaps even the year after. I want to take everything you've seen today, and instead of using a Weibull distribution for the components, use something like a gamma process, and have a degradation path. And now my decision variables, so here we have degradation. My decision variables, so this shows degradation versus time. And when the degradation reaches the purple horizontal line, it fails, and a new one is put in its place. But now the decision variables are not preventive maintenance intervals, they become this, on condition threshold, meaning when I inspect, if it has not yet failed, but it has reached that level, I will replace it. But that's a decision variable. If it's very critical, I can make that low. If it's not critical at all, I can make it the same as the failure threshold. So in my two-stage stochastic model, the second stage variables will be those y's. And let's skip the mathematics. You've seen the fair amount. I hope it wasn't too much. But I can, based on the degradation process, get expected number of inspections, expected downtime, expected cycle duration. We have a new paper, Nushin Yousefi, myself, and it was in December 2019, Reliability Engineering System Safety, where we had a system of degrading components where the degradation paths were dependent, and we selected these inspection intervals. I recommend that paper. And we go through the same third stage, except for now, I'm updating these gamma process parameters. And fourth stage. Let me end. Let me end right here. Oops.
Let me end right there. I know it's traditional to have a slide at the end that says conclusion and then questions, but I don't have those slides. I thought by now you've already seen enough of my slides. So that concludes my presentation. I hope it was interesting. And Professor Shen, could you turn your microphone on and talk?
I'm here. Thanks very much. I learned a lot from your lecture. And so anyone who have questions can communicate with Professor Coit.
And I know it's awkward this way, but I teach my classes this way. I guess probably you guys did the same thing. And so it's difficult. Hello, baby. Oh! I'm Nida. Thank you, very nice talk. So I have a very small question for you, okay? But first, did you hear what I said? I said you need to teach me to speak Chinese for next year. Okay, I have a small question for you. Yes, of course. You mentioned two terms, one term called combined optimal problem. But now most people use joint optimal problem. My question is, two terms are same or different? Say it again. You mentioned combined optimal problem. Yeah, but some people use joint. Yeah, sure. I would think the two terms are same or not. Yeah, so I would say joint would be more mathematical and maybe more rigorous, and combined would be more general, in kind of a more general term. And the way I use them, they're exactly the same. So for me, the reason I use combined, you could pick someone off the street. You could go off the street, and they would understand combined. But joint is so you translate, you use jointly optimization or something. Yeah, I would say, even though I use combined, actually I didn't even think about it. Okay. I would say using the title is about the last thing I do. No, that's not true. That's okay. But so I would say no difference. I would say joint would be more mathematical way of phrasing it. Combined is maybe more, more generally understandable. Okay. Thanks. I'm missing my, oh my goodness. I'm missing my best dinner of the year with Professor Coit. 2 next year. Maybe in coming October, so I can invite you. I hope so. I hope so. Did I see famous Professor Xi?
Yeah, can you hear me?
Yeah, sure.
Yeah, so I guess that I don't really have a question just to say hello to you, but I think I'm the only one here who have met you this year, right?
Right.
Yes.
Yeah.
That was the last year. I came back before everything happened. So
Yang for me was at Rams. From Xinhua. He said when he left for America, he said in Beijing airport, people didn't have masks. He said just 1 week later, he came back, everyone had masks.
Yeah. So in fact, one comment I have is that now there are a lot of funding and research going on related to COVID-19. So in your opinion, what can we do to, have to grab a pie and a piece of this big pie?
All of us, including you, we're not, or maybe I'm not including you, but, people are chasing trends. So I'm working on a proposal now that just very subtly includes COVID-19. We're doing a energy systems optimization. We're considering healthcare costs as part of our objective function. And now we're not saying COVID-19, but we're saying airborne viruses. And then, of course, we're using that as an example. But I don't know. You make me think of, like after the 9/11 terrorist attacks in America, everyone wrote proposals on security. and maybe it feels kind of not so good. So, but already, at least National Science Foundation in America they have what's called RAP, which where they can get a grant very quickly. And so people are already getting funding.
Yeah, that is happening everywhere. In Hong Kong, Singapore, China. So.
We write proposals together. Think of a good idea.
So that's why, if you think about this pandemic, it's basically the stochastic process and network issues. So there are a lot of things that I think we can do with the research we did. So that's why I want to hear if you have any idea and if there are things that we can do.
But it very much could be, this two-stage stochastic optimization. We need to have decisions now for the next one. But then, the decision or the systemic decisions, how to have a safer system. But then you have your stage 2 decisions, which is once the virus occurs, how do you deal specifically with it? So, yeah, you have the idea. I'll do the work.
No, for example, just another example, if we talk about this COVID-19, tests, okay, there are different types of tests. So can we consider those as redundancy, or if there are false positive, false negative? There are a lot of those issues that could be introduced. So,
yeah, kind of like K-version, what's it called? You should know, inversion programming.
I don't know. Okay, very interesting talk. Let's see if others have any technical questions.
谢谢老师。赵老师。
我要说什么？
靠三个赵。
Thanks for talking. It's very interesting. Actually, I have interest on your page 24, component reliability. So that how can you determine for the vibrator distributing the parameter alpha IJK? So I surprised that you publish such kind of papers on IEEE reliability. So I think that it is more suitable for the operations research, these journals. So that my question is, I think that it's very difficult to determine the parameters like alpha, IJK, theta, and beta, IJ.
Yeah, for sure. And so, I mean,
the environment on page 4.
Yeah, I don't have, let me see, I can't see my presentation, but let me go to it.
It's 24.
But so I mean, I can answer two ways. Now, if you give me enough data, and of course the answer is there's no such thing as enough data to do what I'm going to say. Did you say page 24, this one?
Yeah.
So I'm going to answer several ways. One, and before you tell me, I know it's not a good answer. But if you give me enough data, I can set up a likelihood function and estimate every single one of these parameters. But the reason I'm the first to say it's not a good answer is because once you have more than beta, eta, and then you start introducing eta 0 and the alphas, first of all, even if you've had enough data, as my students can tell you, it's very difficult to estimate simultaneously so many parameters. I think early on, I saw that my master's student, Jianhong Li, was watching. If he is, hello, Jianhong. But we had this exact problem. We had a lot of data on the reliability of a steel rebar. That's a piece of metal that goes inside a bridge. And we had lots of data. So we did have enough data to estimate all the parameters, but we couldn't. There was just too much. And so what we had to do, even though we didn't want to, is to take our vector of stresses and say, well, we can't get them all. We can't get them all. We're only going to get those that are most important. So that's a realistic answer. But the truth is, it's hard. Now, the other answer, which is also not so good, but like you said, we could send this to operations research and say, look, this is paper and this model, however I get these parameters, shows the design and preventive maintenance should be done at the same time. And that finding is a central truth. However I get these parameters. And that's a smug answer. You know what I mean? They're smug. That's kind of an intellectual answer. But it's true. It's somewhat true. But the truth is, if little c, the number of stress variables, becomes big, it will be very difficult, even given a large data set. So, what do we do? Well, like reliability engineers have been doing from the earliest days, we do the best we can. We estimate some from data when we can. We make some assumptions. But as you know, and I'm trying not to do this, by the way, often the papers I write, because I'm doing extensions on my own papers, the math gets more and more complicated. And I'm actually trying to stop doing that. Because I have good ideas, but makes the models get bigger. So it's a good question, and I don't have a good answer for you. But I'll say this: people have been doing reliability for a long time, and there almost has never been enough data to estimate all those parameters. So we do the best we can.
Okay. So do we have the previous work on the backward estimation for the random environment?
You mean parameter estimation?
Yeah.
No, but all you have to do, we would look at the observed failures, the observed stresses. We would then treat all the alphas, the eta, and the beta as an unknown parameter. We would then create a likelihood function and we would multiply them all together, take the log of that, and then take all, this is why I say it's difficult to do, and then take partial derivatives with respect to all the unknown parameters and try, anyways, to get likelihood functions. That's what the software like, what's it called? Alta, A-L-T-A, by Reliasoft. That's what it tries to do. You give data in an accelerated life model, which is really what we have here, and it does all the number crunching. and mathematically it's sound.
Yeah.
But practically it's difficult. I know that from experience.
Because now I'm a PhD student, and she said, Professor, now it's not reliability problem, it's operations research problem. So actually, I agree with it. So that if we think that the right distribution is just one factor over your joint optimization, so it seems more easy than mathematical analytics. So my students like that.
Mm-hmm. Well, as you know, I was going to visit you this year. It's not my fault. So I we could have worked on it together.
Oh yes, great. So that I will invite you after this virus situation.
Yes, let's do. So,
okay,
and I mean this to anyone listening. I mean, I'm busy. I have constraints on my time, but I think everyone knows who knows me. You know, if someone wants to talk about research or you know, my papers, you know, we have an expression in America: the door is always open. You know. And that means you're always welcome to ask questions. Again, I'm busy like everybody else. But if someone wants to talk about some interesting research, particularly if it pertains to some of my ideas, you know, I make that time.
OK， 沈老师，再问问其他老师有没有？
谢谢赵老师啊，刘老师来了，刘老师好。
Hello, Professor Coit.
Yes.
Hello.
Professor Liu. Yes, come.
Hello, Professor Coit. Nice to meet you again online. So very nice talk. Yeah, very nice talk. Actually, I read some of your paper presented in the slides, and very good work. So I don't have any question. Just say hello to you, and hope to see you in Xi'an in October.
I hope so. I want to so much, but you know, well, I won't say what's going on in America, but I hope so. That's all I can say. And I'll say further. If I can, I'll be there. That's for sure. You know. It's I hope so. I've only been to Xi'an once, 2011, and let's see, 2011 was Professor Huang had his conference. I think that was Xi'an. So I hope so.
Okay.
I hope I see everyone there.
Okay. Thank you.
Okay. It seems like the technology worked okay. Was everyone able to hear me okay?
Professor, yeah. Let's go.
So were you able to hear me okay?
Oh, maybe she log out, or maybe the website is not good. Yeah. Anyone else have questions about this lecture or about something else? Yeah, so yeah, maybe this way. This time we are finishing. Yeah. Thanks very much, David. It's a long time. I think maybe you are tired.
Little bit.
A very nice talk.
Okay.
Yeah.
So let me
So I should announce the next seminar. So the same time next week, right?
Yeah. So we'll talk tomorrow.
Okay. So this time we finish. Thanks very much.
Okay.
Yeah.
Goodbye, everyone.
So you have to talk tomorrow?
No. We will talk the topic tomorrow, but the seminar is next week.
上面的哦，你们是一系列的事情。
对，我们有4个讲座，然后这个月做2个吧，下个月做2个，然后下一个应该是在下周的同一时间，然后也希望大家都来参加。
这个方法比较好，我们也可以来模仿一下，学习一下。
好的，你要加入我们的讨论吗？明天一起啊？
明天不是明天我要带小孩去那个游乐场。
好的。哎呀，注意疫情啊。
没事，南京好。
好的，行，那谢谢周老师。我们今天先这样吧。谢谢，拜拜。谢谢各位老师，谢谢大家。